Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the radius of this circle that is inscribed by triangle ABC. In the second question, we'll find out the area of rectangle ABCD that blocks this circle. So we start in the first question. In the drawing, we have triangle ABC, side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and our mission is to find out the radius of this circle that is inscribed by triangle ABC. We start with the first method, and here we draw from point C perpendicular on AB. So here this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. In the next step, I'll copy triangle ABD, the great right triangle ABD, and we'll analyze triangle ABD. This is actually triangle BDC. The great triangle is triangle BDC. So this is the right triangle DBC that I copied from the original drawing. In the right triangle DBC, the sum of the angles is equal to 180 degrees. That is to say, 90 degrees plus 60 degrees plus the size of this angle that will define as angle X. In total, they must be equal to 180 degrees. So I write it down. (90 degrees plus 60 degrees plus angle X). In total, they must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. 90 degrees plus 60 degrees is 150 degrees, so I write it down. 150 degrees plus angle X. In total, they must be equal to 180 degrees. Here we'll subtract 150 degrees from this equation. And we'll get that angle X equals to 180 degrees plus 150 degrees. It is equal to 30 degrees. So I found out that the missing angle X is equal to 30 degrees. We'll continue to focus on the right triangle DBC. In the right triangle DBC, sinus 30 degrees is equal to dB over BC. So sinus 30 degrees equals to dB over BC. BC is equal to 2 units, so we substitute BC by 2 and we get that sinus 30 degrees is 1/2, so we substitute sinus 30 degrees by 1/2, and 1/2 equals to dB over 2. Here we will multiply this equation by 2 and we'll get that dB equals to 1 unit. Here dB equals to 1 unit. We continue to focus on the right triangle DBC. In the right triangle DBC, sinus cosine 30 degrees is equal to DC over BC. Okay, so cosine 30 degrees equals to DC over BC, and BC is 2, so we substitute BC by 2. Cosine 30 degrees is square root of 3 over 2, and it is equal to DC over 2. Here we multiply this equation by 2 and we get that DC equals to square root of 3 units. DC equals to square root of 3 units. We found out that angle BCD equals to 30 degrees. So what is the size of this angle? Angle ACD. Angle ACD equals to the big angle ACB minus angle DCB. Again, ACD ACB minus DCB equals to this angle, angle ACD. Angle ACB equals to 75 degrees, angle DCB equals to 30 degrees. 75 degrees minus 30 degrees is 45 degrees. So I found out that angle DCA equals to 45 degrees. In the next step, I will copy the right triangle, triangle ADC in a new page, and we'll analyze triangle DCA. So this is actually the right triangle ADC that I copied from the original drawing. In the right triangle ADC, the sum of the angles is equal to 180 degrees. So each angle we have here, in triangle ADC, we have this angle that is equal to 90 degrees, plus this angle that is equal to 45 degrees, plus the missing angle that we define as angle X. In total, the sum of those three angles must be equal to 180 degrees. "90 degrees plus 45 degrees equals to 135 degrees, so 135 degrees plus X equals to 180 degrees. Here we subtract 135 degrees from this equation, and we'll get that the missing angle, angle X, equals to 180 degrees minus 135 degrees, it is equal to 45 degrees. So angle X equals to 45 degrees. So here we continue to focus on the right triangle, triangle ADC. In the right triangle, triangle ADC, those two angles, they are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of this angle, we have side AD. In front of this angle, we have side DC. And side AD equals to side DC because those two sides are located in front of equal angles, therefore they are equal to each other. But according to what we have already found, out that DC equals to square root of 3 units. So from this equation, AD equals to DC equals to square root of 3 units, we derive that AD is also equals to square root of 3 units. So here AD equals to square root of 3 units. In the next step, we'll implement the Pythagoras theorem on the right triangle, triangle ADC, in order to find out the length of the hypotenuse AC. According to the Pythagoras theorem on the right triangle, triangle ADC, by PT, the derivation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AD squared plus BC squared. So according to equation number 1, AC squared equals to AD squared. AD squared equals to square root of 3 units, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC equals to the square root of 3 squared, therefore DC squared equals to the square root of 3 squared, that is 3. So in conclusion, we found out that AC squared equals to 3 plus 3, that is 6. Here we'll take a look to this equation, equation number 1, and we get that according to equation number 1, AC equals to square root of 6 units. AC equals to square root of 6 units, so we can write here that AC equals to the square root of 6 units. So now we have all the side lengths of all the sides of triangle ABC. Therefore, you actually can implement rule number 5 here, rule number 7. According to rule number 7, if we have a circle with radius r that is described by triangle ABC, that could be any triangle, then the radius of this circle equals to the area of triangle ABC that closes the triangle over the semi-perimeter of triangle ABC. The semi-perimeter of any triangle is equal to the perimeter over 2. So we use this formula in order to find out the radius that we are looking for, the radius of this circle. So according to the new formula, the radius of this circle that we will define as R is equal to the area of this triangle ABC over the semi-perimeter of triangle ABC. Okay, so we use this formula in order to find out the radius that we are looking for, that is the radius of our circle. So we have to find out the area of triangle ABC. And the area of triangle ABC equals to the base of the triangle times the height to the base over 2. Okay, so the area of triangle ABC equals to the base of the triangle. We will take the base as AB, side AB, times the height of the base CD creates 90 degrees with the base, therefore CD is the height of the base over 2. Again, the area of triangle ABC equals to the base, that is AB, times the height of the base, that is CD over 2. So what is the value of AB? AB equals to 1 plus square root of 3 units. What is the value of CD? CD equals to square root of 3 units, all divided by 2. So here we'll open the brackets and we get that square root of 3 times 1 is square root of 3 plus square root of 3 times square root of 3 is 3 over 2. And square root of 3 plus 3 over 2 is 2.366. So found out that the area of triangle ABC is equal to 2.366 square units. The next step we find out the semi-perimeter of triangle ABC. The semi-perimeter of any triangle is equal to the perimeter over 2. And the perimeter of triangle ABC equals to the sum of its sides, that is to say it is AB plus AC plus BC divided by 2. Here the same perimeter of triangle ABC equals to the sum of its side lengths over 2. AB equals to 1 plus square root of 3 units times AC, that is equal to square root of 6 units plus square root of 6 units plus BC, that is equal to 2 all divided by 2. So here S equals to, actually here we have in total this expression equals to 3.59 units, and therefore we get that the radius of the circle that is described by triangle ABC is equal to R equals to the area of triangle ABC over S. The area of triangle ABC equals to 2.366 square units over the semi-perimeter of triangle ABC, that is equal to 3.59 units, and this is equal to 0.6589 units. Okay, so the radius of this circle that is described by triangle ABC equals to 0.6589 units. We finished with the first method. In the next step, I will present to you the second method. So in the second method, we define the center of the circle as O. We define the point of tendency of tangent BC with this circle as D. We join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that we will define as R. And we have the radius OD that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle also will be equal to 90 degrees according to rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. We join points O and C together by a straight line. We join points O and B together by a straight line. We define the point of tendency of tangent AB with this circle as E. We join points O and D together by a straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of the circle that is equal to R. Here the radius OE is drawn to the point of tendency, therefore this angle will equal to 90 degrees, and this angle will also equal to 90 degrees according to rule number 1. We define the point of tendency of tangent AC with this circle as F. We join points O and F together by a straight line. Again, point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle that is equal to R. And we have the radius OF that is drawn to the point of tendency, therefore this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees according to number 1. So here we actually have also rule number 2, according to rule number 2, a tangent to the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point P. From the common external point P, we have two tangents to this circle, tangent PB and tangent PA. And according to rule number 2, the lengths of those two tangents are equal to each other, that is to say PA equals to PB. We actually can implement rule number 2 in our drawing, because if we focus on the common external point B, from the common external point B, we have two tangents to the circle, tangent BE and tangent BD. And according to rule number 2, the lengths of two tangents are equal to each other, that is to say BE equals to BD. Okay. Likewise, if we focus on the common external point C, from the common external point C, we have two tangents to this circle, tangent CD and tangent CF. And according to rule number 2, they are equal to each other. That is to say, CF is equal to DC. In the next step, we will prove that the green triangle OD, BOD, this green triangle is congruent to the orange triangle OBE. So why those two triangles congruent to each other? So I write it down. Triangle OBD, triangle OBE. So why the green triangles can go into the orange triangle? First of all, we just right now found that BD equals to BE. According to rule number 2, BD equals to BE. In addition, OD equals to OE, and they are both the radii of the circle, it is equal to R. And finally, OB is the common side that belongs to both triangles, so OB equals to itself. It's a common side that belongs to both triangles. So it actually proves that the green triangles can go into the orange triangle according to side rules. So I write it down. The green triangle OBD is congruent to the orange triangle OB according to side rule. And from the fact that those two triangles can go into each other, and conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So here angle EBO in the orange triangle is equal to angle OBD in the green triangle. So if we define angle OBE as alpha, then from this equation we get that angle EBO is also equals to alpha. So both those two angles are equal to alpha, therefore the sum of those two angles is alpha plus alpha, and according to what is given as the equation, alpha plus alpha equals to 60 degrees. Alpha plus alpha is 2 alpha, so 2 alpha equals to 60 degrees. We divide this equation by 2 and we get that alpha equals to 30 degrees. Okay, alpha equals to 30 degrees. So to write here that this is angle alpha, it is equal to 30 degrees, and this is angle alpha that is also equals to 30 degrees in its size. Okay. Actually, it is very easy to prove that those two triangles are also congruent to each other according to side rule, and from that fact we will conclude that those two angles are equal to each other. So here angle OCD is equal to this angle, it is actually angle OCF. Okay, angle OCD equals to angle OCF. According to the rule that corresponding angles in congruent triangles are equal to each other. Okay. So if we define angle OCF as theta, then from this equation we get that angle OCD is also equals to theta. So actually those two angles, they are both equal to theta. The sum of those two angles is theta plus theta, that is equal to 75 degrees according to what is given as the question. So theta plus 2 theta is theta plus theta is 2 theta, and 2 theta equals to 75 degrees. Here we divide this equation by 2 and we get that angle theta equals to 37.5 degrees. Okay. This angle theta equals to 37.5 degrees, and this angle theta also equals to 37.5 degrees. In the next step, we focus on the green triangle OBD, in triangle OBD, in the right green triangle OBD, tangents 30 degrees, equals to OD over BD. Repeat again. The right triangle OBD, tangents 30 degrees, equals to OD over BD. OD equals to R over BD. So here we multiply this equation by BD and then we divide it by tangents 30 degrees and we get that BD is equal to R over tangents 30 degrees. In the next step, we'll focus on the yellow triangle ODC. In the yellow triangle ODC, tangents 30 degrees, is equal to OD over DC. OD equals to R, so we substitute OD by R over DC. So in conclusion, we found out that in the yellow triangle ODC, tangents 30 degrees equals to R over DC. Here we'll multiply this equation by DC and then we divide it by tangents. So actually here is not tangents 30 degrees, but it is tangents 37.5 degrees. So I correct it to tangents 37.5 degrees. So here, so as I mentioned before, we will multiply this equation by DC and then we divide it by tangents 37.5 degrees and we get that DC is equal to R over tangents 37.5 degrees. Okay, so we have the values of BD and DC. From the drawing, it is very easy to see that BC equals to BD plus DC again. BC equals to BD plus DC here. BC equals to BD plus DC. So here BC is equal to BD and BD is R over tangents 30 degrees plus DC. DC is equal to R over tangents 37.5 degrees. Okay. So here we take R as a common factor out of those two expressions, and then we get that BC equals to 2, so we substitute BC by 2, so 2 equals to R is a common factor. What is left from this expression after 2 from it, R is a common factor. What is left is actually 1 over tangent 30 degrees. And what is left from this expression after 2 from it, R is a common factor. What is left is actually 1 over tangents 37.5 degrees. Okay, so here we find out the value of 1 over tangent 30 degrees, the value of 1 over tangent 37.5 degrees. We add the two numbers together, and in this way we find out the radius that we are looking for, that is the radius of this circle that is described by triangle ABC. So we get that 2 equals to R, 1 over tangent 30 degrees is 1.372 plus 1 over tangent 37.5 degrees is 1.303. So we found out that 2 equals to R times 3.035. We divide this equation by 3.035 and we get that R equals to 0.696589. The radius of the circle is equal to 0.6589 units. We finished with the first, actually finished with the second method of question number 1. We finished with question number 1. In the next step, I present to you the second question, and we solve the second question in two different methods. In the drawing we have rectangle ABCD. Inside rectangle ABCD we have a circle. Chord PS equals to 6 units, chord QS equals to 5 units. And our mission is to find out the area of this rectangle ABCD. So first of all, we define the center of the circle as point O. Here point O is the center of the circle. We know that all the angles inside the rectangle are right angles, so this angle equals to 90 degrees, this angle equals also to 90 degrees, this angle equals to 90 degrees, and this angle is also equals to 90 degrees. We define side AB of the rectangle as A. We define side BC, the width of the rectangle as B. BC is also the diameter of the circle, so I write it down. It is very easy to prove that BC is the diameter, but we will not do it. We join points O and P together by a straight line. Point O is the center of the circle. Point P is the point of the circle itself, therefore OP is the radius of the circle that we will define as R. If the diameter of the circle is B, then the radius will be equal to half of it, that is to say it will be equal to b over 2. The next step, I'll present to you rule number 4 and we'll implement rule number 4 in our drawing. According to rule number 4, the perpendicular from the center of the circle to a chord bisect the chord. O is the center of the circle, and the perpendicular from the center of the circle is the perpendicular OM. This perpendicular bisects chord CD, that is to say CM equal to CD according to rule number 4. We can implement rule number 4 in our drawing. Here from the center of the circle, that is to say from point O, we'll draw perpendicular on chord SP. So here this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord SP, SM. According to rule number 4, the perpendicular OM bisects chord PS. The perpendicular OM bisects chord PS. That is to say, SM equals to MP. SM equals to MP according to rule number 4. So if we define MP as X, MP equals to X according to our definition, then from this equation SM equals to MP equals to X, we derive that SM is also equals to X. Here SM equals to X. So here X plus X is equal to SP. X plus X equals to SP. X plus X is 2X, that is equal to SP. But SP equals to 6 units according to what is given as the equation. From this equation 2x equals to SP equals to 6, we derive that 2x equals to 6. We divide this equation by 2 and we get that x equals to 3 units. Here x equals to 3 units. Okay. In the next step, we define the point of tendency of tangent DC with this circle as point F. We join points O and F together by a straight line. Point O is the center of the circle. Point F is the point on the circle itself. Therefore, OF is the radius of the circle, that is equal to R. We have the radius OF that is drawn to the point of tendency. Therefore, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. This angle equals to 90 degrees, and this angle also equals to 90 degrees. So, here also we have the radius OP that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So, inside quadrilateral OPFC, we have 1, 2, 3 right angles, and any quadrilateral that has 3 right angles, the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in the quadrilateral to 360 degrees, this angle must be equal to 90 degrees. So inside quadrilateral OPFC we have 4 right angles. Okay? And any quadrilateral that does 4 right angles must be at least a rectangle, if not a square. So actually quadrilateral OPFC is a rectangle. So in the next step, from this point Q, we go perpendicular on BC. I repeat again, from this point Q, we'll go perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point Q and BC as T. We define the intersection point between the perpendicular QT and the radius OF as L. Inside quadrilateral QPLT, this quadrilateral, we have 1, 2, 3 right angles, and any quadrilateral that has 3 right angles, the fourth angle must be also a right angle. So this angle, the fourth angle, it is equal to 90 degrees. So actually inside quadrilateral OPLT, we have 4 right angles, therefore quadrilateral OPLT is a rectangle. Why? Because it has 4 right angles. I'll repeat again. Quadrilateral OPLT is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, OP equals to LT. We also know that the opposite sides of a rectangle are parallel to each other. That is to say, OP is parallel to LT. I repeat again, in rectangle OPLT, its opposite sides are parallel to each other. That is to say, OP is parallel to LT. But what is OP? What is line segment TL? It is one side of rectangle OPTL, but it is also part of perpendicular QT. It is part of perpendicular QT. QT is a perpendicular, it is absolutely a straight line. So I write it down. QT is a perpendicular, therefore it is a straight line. Perpendicular QT is a straight line. Okay, so QT is a straight line and LT is part of the straight line QT. And if part of a straight line LT is parallel to OP, it means that the straight line itself QT must be also parallel to OP. Very simple. If part of the straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. That is to say, QT is also parallel to OP. QT is also parallel to OP. Okay, QT is parallel to OP, and we have here new rule that is actually rule number 9. According to rule number 9, alternating angles between parallel lines are equal to each other. Here, line A is parallel to line B. Those two pink angles are defined as alternating angles, and therefore, because of the fact that they are located between parallel lines, they are equal to each other according to rule number 9. Okay, we can implement rule number 9 in our drawing. Why? Because in our drawing we have line OP is parallel to line QT, and those two angles are defined as alternating angles, and are located between the parallel lines OP and QT, therefore they are equal to each other according to rule number 9. So I write it down. This angle, that is actually angle OPQ, it is equal to this angle, that is actually angle PQT. I repeat again, angle OPQ equals to angle PQT. Why? Because there are those angles are two alternating angles that are located between the parallel lines OT and PQ, OT and OP, therefore they are equal to each other according to rule number 9. So if we define angle PQT as theta, here angle PQT, angle PQT, this angle equals to theta according to our definition. Then from this equation, angle OPQ equals to angle PQT equals to theta, we will derive that angle OPQ is also equals to theta. Angle OPQ is also equals to theta. Here, this angle OPQ is equal to theta. Okay. In the next step, we'll focus on quadrilateral QDTC. In quadrilateral QDTC, we have 1, 2, 3 right angles. And any quadrilateral that has 3 right angles, the fourth angle must be also a right angle. So this is the fourth angle, that it must be a right angle, it must be equal to 90 degrees. So quadrilateral QTTC is 4 right angles, therefore it is a left angle. And we know that the opposite sides of a left angle are equal to each other. That is to say, QT equals to DC. QT equals to DC in rectangle QT DC. In rectangle QT DC, QT equals to DC. QT equals to DC. But we know it is given as an equation that ABCD is a rectangle, and the opposite sides of a rectangle ABCD are equal to each other. That is to say, DC is equal to AB. You can write here that DC equals to AB. And from this equation, QT equals to DC equals to AB, we will derive that QT is also equals to AB. QT is also equals to AB, but according to our definition, AB equals to A. So you can write here that AB equals to A, and for this equation QT equals to AB equals to A, we will derive that QT equals to A. QT equals to A. Here we can write down that QT equals to A. In the next step, we'll focus on the right green triangle OMP. I will copy triangle OMP in a new page and we'll analyze triangle OMP. Okay, so angle OMP equals to 90 degrees. MP equals to 3 units, and the hypotenuse OP equals to B over 2. Is the radius of the circle. And finally, angle OPM, this angle, or QPO is equal to theta. So this is the right triangle OPM that I copied from the original drawing. In the right triangle OPM, it is very easy to see that cosine theta equals to MP over OP. Again, cosine theta equals to MP over the hypotenuse OP. So I write it down. Here, equation number 1 that states that cosine theta equals to MP over OP. But here MP equals to 3, so we'll substitute MP by 3, and OP equals to B over 2, so we'll substitute OP by B over 2. Here 2 moves to the numerator, 2 times 3 is 6, and B moves to the denominator, so we'll get that cosine theta equals to 6 over B according to equation number 1. In the next step, we'll focus on the right big triangle PQT. On the right big triangle QPT. What is the value of cosine theta? Here, the value of cosine theta is equal to QT over QP. I repeat again. In the right big triangle QTP, QPT, cosine theta equals to QT over QP. We have already found out that QP equals to A, QT equals to A, we substitute QT by A. What is the value of QP? QP equals to 5 plus 6. Again, QP equals to 5 plus 6, that is 11, so we substitute QP by 11. So in conclusion, we found out that according to equation number 2, cosine theta equals to A over 11, we have two different expressions for cosine theta, therefore we create equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Okay, and cosine theta according to equation number 1 is equals to 6 over b, and it must be equal to cosine theta according to equation number 2, that is equal to a over 11. So in conclusion, found out that according to equation number 3, 6 over b equals to a over 11. Here we cross multiply this equation number 3, and we get that a times b, it is equal to 6 times 11, that is 66. So in conclusion, found out that according to equation number 3, a times b equals to 66. So in the next step, we find out the area of rectangle ABCD. The area of rectangle ABCD, it is equal to the length of the rectangle times the width. That is the area of any rectangle. So the length is AB and the width is BC, so it is AB times BC. AB is A and BC is B according to our definition, and we just right now found out that AB equals to 66, so we can write down that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD, it is equal to 66 square units. Okay, we finished the first method. In the next step, I present to you how to find out the area of rectangle ABCD according to the second method. Okay. In the second method, we define the center of the circle as O. We know that all the angles inside the rectangle are right angles, so here this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees. And this angle is also equals to 90 degrees. We'll define side AB of rectangle ABCD as A. We'll define the width BC as B. And I've already mentioned in the first method that BC that is equal to B is also the diameter of the circle, so I write it down. We join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. We define the radius as R. If the diameter of the circle is B, then the radius will be half of it, that is B over 2. So R equals to B over 2. Here we'll extend the radius PO until it touches side AD of rectangle ABCD. We'll define the touching point of the extended radius PO and AD as point F. Here I already mentioned in the first method that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. So here we'll focus on quadrilateral ABPF. In quadrilateral ABPF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees in quadrilateral ABPF. Likewise, in quadrilateral FPDC, this quadrilateral, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. We define the touching point of the extended radius PO and the circle as point S. It's point G. We define it as point G. Here we join points G and S together by a straight line. What is the definition of chord GP? We know that chord GP passes through the center of the circle, that is point O. Any chord that passes through the center of the circle must be the diameter of the circle. So GP is the diameter of the circle. Diameter, and the diameter of the circle equals to B, according to what we have already found out. Here we have peripheral angle GSP that rests on GP, that is the diameter of the circle. And we actually have rule number 5 that relates to peripheral angle that rests on the diameter of the circle. According to rule number 5, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. Here the diameter of the circle is AB and peripheral angle AMB rests on the diameter AB, therefore it is equal to 90 degrees. We can implement rule number 5 in our drawing, because in our drawing we have peripheral angle PSG that rests on GP, that is the diameter of the circle, therefore peripheral angle PSG equals to 90 degrees according to rule number 5. So we'll focus on triangle GSP. Triangle GSP will define this angle as theta. So in triangle GSP we have this angle that is theta, this angle is 90 degrees, so this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle QFP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, exactly for the same reason that this angle must be equal to 90 degrees minus theta. So in the next step, we'll prove that the green small right triangle GSP is similar to the big right triangle QFP. So I write it down. We'll prove that the big right triangle FQP, this big right triangle FQP is similar to the small right green triangle GSP. So why those two triangles are similar to each other? First of all, those two angles are equal to 90 degrees minus theta, therefore they are equal to each other. So here, this angle is FQP is equal to this angle that is actually angle SGP Repeat again. Angle FQP equals to angle SGP. They are both equal to 90 degrees from center, therefore they are equal to each other. In addition, we have those two angles that are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle QFP, and it is equal to this angle that is actually angle GSP. Repeat again, angle QFP equals to angle GSP, they are both equal to 90 degrees, therefore they are equal to each other. And finally, we have this angle theta is a common angle that belongs to both triangles, so angle theta is angle QPF, and it is equal to itself. You can call angle theta also as angle SPG. Two different names for the same angle. Okay, so repeat again, angle QPF equals to angle SGB, so angle theta equals to itself. It's a common angle that belongs to both triangles, so we actually proved that the big right triangle FQP is similar to the small green right triangle QGSP according to angle similarity rule. Triangle FQP is similar to the small right green triangle GSP according to angle similarity rule. And for the fact that those two triangles are similar to each other, we derive the following relationship exists between their sides. We will conclude that FP, the side of the big right triangle, over SP, that is the side of the small right green triangle, is equal to QP in the big right triangle, the hypotenuse in the big right triangle, over GP. Repeat again. I found out that according to equation number 1, FP over SP equals to QP over GP. Okay. So here we have FP. So here we know that quadrilateral ABFP is a rectangle because it has 4 right angles, and the opposite sides of a rectangle are equal to each other. AB equals to A according to our definition, and AB also equals to FP. Therefore, FP must be also equal to A. If FP equals to AB and AB equals to A, therefore FP must be also equal to A. Okay, so FP equals to A. So we substitute FP by A over SP. SP is equal to 6 units according to what is given as the question. And it is equal to QP. QP, what is the length of QP? It is very easy to see from the drawing that QP equals to 5 plus 6. Again, QP equals to 5 plus 6, that is 11. So we substitute QP by 11 over GP. What is the value of GP? The value of GP is the diameter of the circle, that is equal to B. So we substitute GP by B. So in conclusion, we found out that according to equation number 1, A over 6 equals to 11 over B. Here we cross multiply this equation, equation number 1, and we get that according to equation number 1, A times B equals to 6 times 11, that is 66. So AB equals to 66. And what is the area of rectangle ABCD? The area of rectangle ABCD equals to the length of the rectangle, that is AB, times the width, that is BC. According to our definition, AB equals to A and BC equals to B. So ABCD, the area of ABCD is AB, but we just like now found out that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD is equal to 66 square units. Okay, we finished with the second method. In the next step, I will summarize the lecture. We start with the first question, of course. So in the drawing, we have triangle ABC. Side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 30 degrees, and our mission is to find out the radius of this circle that is described by triangle ABC. We started with the first method. From point C, we drew perpendicular on AB, so this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. Then I copied the green triangle DBC in the new page and analyzed triangle DBC. This is the right triangle DBC that I copied from the original drawing. In the right triangle DBC, this angle equals to 90 degrees, this angle equals to 60 degrees, and define the missing angle as x. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here 90 degrees plus 60 degrees plus the size of angle x must be equal to, in total, to 180 degrees. 90 degrees plus 60 degrees is 150 degrees, so 150 degrees plus x in total must be equal to 180 degrees. Here we subtracted 150 degrees from this equation and we found out that x, the size of x, is 180 degrees plus 150 degrees, that is 30 degrees. Okay? So here we continue to focus on the right triangle BDC. In the right triangle BDC, we know that sinus 30 degrees equals to BD or BC. BD is BD and BC is 2, so we substitute BC by 2. Sinus 30 degrees is 1/2, so we substitute sinus 30 degrees by 1/2. So according to this equation, 1/2 equals to BD over 2. We multiply this equation by 2 and we found out that BD equals to 1 unit. Here, BD equals to 1 unit. We continue to focus on the right triangle BDC. On the right triangle BDC, cosine 30 degrees equals to DC over BC. Again, cosine 30 degrees equals to DC over BC. So, cosine 30 degrees equals to DC over BC, but BC is 2, so we substitute BC by 2. And cosine 30 degrees is square root of 3 over 2. So square root of 3 over 2 equals to DC over 2. We multiply this equation by 2 and we found out that DC equals to square root of 3 units. Here, DC equals to square root of 3 units. Then we found out the size of this angle ACD. Angle ACD equals to the big angle, that is angle ACB, minus the smaller angle, that is angle DCB. That is to say, it is equal to the size of the angle that is 75 degrees minus the small angle that is 30 degrees. 35 degrees minus 30 degrees, 75 degrees minus 30 degrees is 45 degrees. Then I copied triangle ADC in a new page and analyze triangle ADC. This is the right triangle ADC that I copied from the original drawing. This angle equals to 90 degrees. This angle equals to 45 degrees. This is the missing angle X. In the right triangle ADC, 90 degrees plus 45 degrees plus this angle that is defined as X. In total, they must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, and 135 degrees plus X must be equal to 180 degrees. We subtracted 135 degrees from this equation and we found out that the missing angle X equals to 180 degrees minus 135 degrees, it is 45 degrees. So this angle equals to 45 degrees. We continue to focus on the right triangle ADC. In this right triangle, those two angles are equal to each other. They are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle there are equal sides. So in front of this angle we have side DC. In front of this angle we have side AD. And those two sides must be equal to each other because they are located in front of equal angles. So AD equals to DC. But we have already found out that DC equals to square root of 3 units. So from this equation AD equals to DC equals to square root of 3 units. We will derive that AD also equals to square root of 3 units. Here AD is also equal to square root of 3 units. Okay, in the next step, we implemented the Pythagoras theorem on the right triangle ADC in order to find out the value of the hypotenuse. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. So AC square equals to AD square. AD is square root of 3, therefore AD square is square root of 3 squared, that is 3. Plus DC square. DC is square root of 3, so DC square is square root of 3 squared, that is also 3. So in conclusion, we found out that AC square equals to 3 plus 3, and 3 plus 3 is 6. Here we took out of this equation number 1, and we found out that AC equals to the square root of 6 units. Here AC equals to the square root of 6 units. Then I presented to you a new formula that will help us to find out the radius of this circle that is described by triangle ABC. The radius of the circle that is described by triangle equals to the area of the triangle of the semi-perimeter of the triangle that blocks the circle. And the semi-perimeter of any triangle is equal to the perimeter over 2. So what is the area of triangle ABC? The area of triangle ABC equals to the base times the height over 2. The base is AB, the height is CD, all divided by 2. AB equals to 1 plus square root of 3 units, CD equals to square root of 3 units over 2. We open the brackets here, we got that 1 times square root of 3 is square root of 3, and square root of 3 times square root of 3 is 3. So square root of 3 plus 3 over 2 is equal to 2.366 square units. So the area of triangle ABC equals to 2.366 units. And what is the semi-perimeter of triangle ABC? The semi-perimeter of triangle ABC equals to the perimeter that is the sum of its sides over 2. The sum of its sides is AB plus AC plus BC. If you divide it by 2, you get the semi-perimeter. Side AB equals to 1 plus square root of 3. Side AC equals to square root of 6 units, and side BC equals to 2. All divided by 2. The value of this expression equals to 3.59 units, and therefore the radius of the circle that is described by triangle ABC equals to the area of triangle ABC, that is 2.366 square units over the semi-perimeter of triangle ABC, that is 3.59 units. And here 2.366 over 3.59 equals to 0.6589 units. Okay, so we finished with the first method. Then I presented to you how to find out the radius of this circle according to the second method. In the second method, we define the center of the circle as point O. We join points O and F together, points O and C together, points O and T together, points O and E together, and points O and B together. Those three angles, they are both equal to 90 degrees, according to rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius. The same thing is true for OF and OD, they are all the radii of the circle. And then also presented to you rule number 2, that the lengths of two tangents from a common external point to a circle are equal. We implemented here rule number 2, we have the common external point, point B. From the common external point, point B, we have two tangents to the circle, tangent BE and tangent BD, therefore they are equal to each other according to rule number 2. Likewise, from the common external point, point C, we have two tangents to the circle, tangent CF and tangent CD. They are equal to each other according to rule number 2. Then we proved that the green triangle is congruent to the orange triangle. Why? Because those two sides are equal to each other according to rule number 2. Those two sides are both the radii of the circle, therefore they are equal to each other. And side OB is the common side that belongs to both triangles, so those two triangles can go into each other according to side rule. And for the fact that those two triangles can go into each other, we conclude that those two angles are equal to each other. So if one angle is alpha, then the other angle must be also alpha. And the sum of those two angles, alpha plus alpha, must be equal to 60 degrees according to what is given as the question. So 2 alpha equals to 60 degrees, it means that alpha equals to 30 degrees. So here alpha equals to 30 degrees, and this angle alpha equals also to 30 degrees. Likewise, it is very easy to prove that those two triangles also can go into each other according to side rule. From the fact that those two triangles can go into each other, we will derive that those two angles also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define one angle as theta, then the other angle must be also equal to theta, because they are equal to each other. So theta plus theta equals to 75 degrees according to what is given as a question. 2 theta equals to 75 degrees. We divided this equation by 2 and found out that theta equals to 37.5 degrees. Here theta equals to 37.5 degrees, and this angle theta is also equal to 37.5 degrees. Then we focus on the green right triangle OBD. In the green right triangle OBD, tangent theta equals to OD over BD. Tangent theta equals to tangent 30 degrees, of course here tangent 30 degrees, it is equal to OD over BD. OD is R, BD is BD. Here we multiplied this equation by BD and we divided by tangent 30 degrees, and we found out that BD equals to R over tangent 30 degrees. Likewise, we focused on the yellow triangle, yellow right triangle ODC. The yellow right triangle ODC, tangent 37.5 degrees equals to OD over DC. Again, tangent 37.5 degrees equals to OD over DC. OD is R over DC. We multiplied this equation by DC and then we divided by tangent 37.5 degrees and found out that DC equals to R over tangent 37.5 degrees. So we have the values of VD and DC, and it is very simple to see that VC equals to BD plus DC. Again, BC equals to BD plus DC. BD is R over tangent 30 degrees, DC is R over tangent 37.5 degrees. We took R as a common factor, and we got this expression. 1 over tangent 30 degrees is 1.732 units, and 1 over tangent 37.5 degrees is 1.303. And 1.732 plus 1.303 is 3.035. We divided this equation by 3.035 in 035, and found out that the radius of the circle that we are looking for it is equal to 0.6589 units. And we got to the sum results in both methods. We finished with the first question, then I presented to you the second question, and we solved the second question in two different methods. So in the drawing we have rectangle ABCD. Inside rectangle ABCD we have a circle. Chord SP equals to 6 units, line segment QS is 5 units, and our mission is to find out the area of rectangle ABCD. We define the center of the circle as point O. We defined AB as A, BC as B, and BC that is equal to B, it is also the diameter of the circle. So here we join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. Here point O is the center of the circle, point F is the point of the circle itself, therefore OF is also the radius of the circle. This angle equals to 90 degrees according to rule number 1, and this angle equals to 90 degrees according to rule number 1. Okay, then I presented to you rule number 4, and we implemented rule number 4 in our drawing. From the center of the circle, that is point O, we draw perpendicular on chord SP. According to rule number 4, chord OM, the perpendicular OM bisects chord SP. That is to say, SM equals to MP. Okay, SM equals to MP. SM equals to MP. And so if MP equals to X, then from this equation SM equals to MP equals to X, so we derive that SM is also equals to X. So SM equals to X and MP equals to X, therefore X plus X equals to SP, X plus X is XP, so X plus X is 2X, that is equal to SP, but SP equals to 6 units according to what is given as the equation. So from this equation 2x equals to xp equals to 6, we derive that 2x equals to 6, we divided this equation by 2 and we found out that x equals to 4 units. Here x equals to 4 units and x equals to 4 units. Then here we have quadrilateral OPFC. In quadrilateral OPFC we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees. This angle must be equal to 90 degrees. Then from point Q we draw perpendicular on BC. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as T. So in quadrilateral OP LT we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. So quadrilateral OPLT has 4 right angles, therefore it is a rectangle, and the opposite sides of a rectangle are parallel to each other. That is to say, side OP of rectangle OPLT is parallel to side LT. But what is LT? LT is part of perpendicular QT. And QT is a perpendicular, it is absolutely a straight line. So QT is a straight line, and part of the straight line QT that is LT is parallel to OP. So if part of a straight line is parallel to OP, then the straight line itself, QT, must be also parallel to OP. Why? Because if a part of a straight line is parallel to another straight line, it means that the straight line itself must be also parallel to the other straight line. Okay, therefore, here we can actually conclude from it that OP is parallel to QT. OP is parallel to QT. Here OP is parallel to QT. OP is parallel to QT. Here OP is parallel to QT. And we have here rule number 9. According to rule number 9, alternating angles between parallel lines are equal to each other. Those two angles are defined as alternating angles and they are located between the parallel lines OP and QT, therefore they are equal to each other. So here those two angles are equal to each other according to rule number 9. That is to say, angle OPQ is equal to angle PQT according to rule number 9. So if we define angle PQT as theta, if this angle equals to theta, then from this equation angle OPQ equals to angle PQT equals to theta, we derive that angle OPQ is also equal to theta. If this angle is also equals to theta. Okay. Then we focused on quadrilateral QTDC. Inside quadrilateral QTDC, this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also right angle. Any quadrilateral that has 4 right angles must be at least a left angle. So here, quadrilateral QTDC is a left angle. In left angle QTDC, the opposite sides are equal to each other. That is to say, DC is equal to QT. DC is equal to QT, but here it is given as the equation that ABCD is left angle. And the opposite sides of left angle ABCD are equal to each other. That is to say, DC equals to AB. So we can write here that DC equals to AB, and from this equation QT equals to DC equals to AB, we will derive that QT is also equals to AB. QT equals to AB. But according to our definition, AB equals to A. So from this equation QT equals to AB equals to A, we will derive that QT is also equals to A. Here, QT is also equals to A. Okay, then I copied the right green triangle OMP in the new page and analyze triangle OMP. This is the right triangle OMP that I copied from the original drawing. This again equals to theta, MP equals to 3, or the hypotenuse OP equals to P over 2. So here cosine theta equals to PM over PO. Cosine theta equals to MP over OP. Cosine theta equals to MP over OP. MP equals to 3, so we substitute MP by 3. OP equals to B over 2, we substitute OP by B over 2. 3 over B over 2 equals to 6 over B. So according to equation number 1, we found out that cosine theta equals to 6 over B. Then we focused on the big right triangle, triangle PTQ. In the big right triangle PTQ, cosine theta equals to QT over QP. Again, cosine theta equals to QT over QP. Cosine theta equals to QT over QP. QT equals to A. QT equals to A. And what is the value of QP? QP equals to 5 plus 6, that is 11. QP equals to 11. So in conclusion, I found out that according to equation number 2, cosine theta equals to A over 11. So we have two different expressions for cosine theta, therefore we create equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. Cosine theta according to equation number 1 equals to 6 over b, and it must be equal to cosine theta according to equation number 2 that is equal to a over 11. So according to equation number 3 we found out that 6 over b equals to a over 11. Here we cross multiply this equation number 3 and found out that a times b equals to 6 times 11, that is 66. So according to equation number 3 we found out that ab equals to 66. And then the area of rectangle ABCD equals to the length of the rectangle times the width. The length is AB, the width is BC. According to our definition, AB equals to A and BC equals to B. So in conclusion, found out that the area of rectangle ABCD equals to A times B. But we just right now found out that AB according to equation number 3 equals to 66. So we can write that AB equals to 66. So in conclusion, found out that the area of triangle ABCD equals to 66 square units. We finished with the first method, then I presented to you how to find out the area of this rectangle ABCD according to the second method. In the second method, we define the center of the circle as O. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius. All the angles inside the rectangle are right angles. AB equals to A and BC equals to B according to our definition, and BC is also the diameter. So if the radius is R and BC that is equal to B is the diameter, it means that the radius will be half of the diameter that is B, that is to say R equals to B over 2. OP is the radius, and according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then we extended the radius PO until it touches the side AD of rectangle ABCD at point F. Okay, so here in rectangle FBCD we have 1, 2, 3 right angles, therefore the fourth angle must be a right angle. This angle equals to 90 degrees. Likewise in rectangle VAPF we have 1, 2, 3 right angles, therefore the fourth angle, this angle must be also equal to 90 degrees. Okay, so for the lateral ABFP has 4 right angles, therefore it is a rectangle, and the opposite sides of a rectangle are equal to each other. That is to say, AB equals to FP. But AB equals to A, therefore FP must be also equal to A. Okay, then actually I presented to you rule number 5. Here we join points D and S together by a straight line. Chord PG, what is the definition of chord PG? Any chord that passes through the center of the circle must be the diameter of the circle, therefore PG that passes through point O is the diameter of the circle, therefore PG equals to the diameter that is equal to B. According to what we have already found out, the diameter of the circle is B. Okay, we join points G and S together by a straight line. In this way we created peripheral angle GSP that rests on the diameter, and according to rule number 5, any peripheral angle that rests on the diameter must be equal to 90 degrees. So this peripheral angle that rests on GP, that is the diameter of the circle, equals to 90 degrees. So this angle equals to 90 degrees. We define this angle as theta, therefore this angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 180 degrees, the sum of the angles in any triangle. Likewise, in the right triangle FPQ, this angle equals to 90 degrees. This angle equals to theta, therefore this angle must be equal to 90 degrees, exactly for the same reason that this angle equals to 90 degrees. To 90 degrees minus theta, exactly for the same reason that this angle also equals to 90 degrees minus theta. Then we prove that those two triangles are similar to each other according to according to angle rule. Those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. Those two angles, they are both equal to 90 degrees, therefore they are equal to each other. This angle is a common angle that belongs to both angles, so this angle equals to itself. So we actually proved that the big right triangle FQP is similar to the small green right triangle GSP according to angle similarity rule. And from the fact that those two triangles are similar to each other, we conclude that following relationship exists between their sides. We conclude that FP over SP equals to QP over GP. FP, what is the value of FP? FP is A. Substitute FP by A. What is the value of SP? SP is 6. So substitute SP by 6. What is the value of QP? QP equals to 5 plus 6, that is 11. So substitute QP by 11. What is the value of GP? GP is the diameter of the circle, that is equal to B. So substituted GP by B. So in conclusion, we found out that according to equation number 1, A over 6 equals to 11 over B. Because multiplied this equation number 1, and we found out that AB equals to 66. Okay. What is the area of rectangle ABCD? The area of rectangle ABCD equals to the length of the rectangle, that is AB, times the width, that is BC. AB equals to A and BC equals to B according to our definition. So in conclusion, we found out that the area of the rectangle ABCD equals to A times B, and we just right now found out that A times B is equals to 66. Here, according to equation number 1, we found out that A times B equals to 66. So in conclusion, we found out that the area of rectangle ABCD is equal to 66 square units. So in both methods, we found out that the area of this rectangle ABCD is equal to 66 square units. Likewise, we found out in both methods of question number 1 that the radius of the circle that is described by triangle ABC, it is equal to 0.6589 units in both methods. Okay, thank you very much.